Right.
Yes, sir.
So yeah, let's see what you're saying about adjoints.
So the determinant of the k adjoint, so that is the taking the adjoint of the matrix A k times. So like adjoint cube would be adjoint of adjoint of adjoint of A. So something like that.
Okay.
So yeah, the determinant of this k times
Wait.
uh,
So
it,
so just recall me. So the definition of adjoint is
oh, the adjoint is the inverse. I mean, sorry, not inverse. It's the transpose of the matrix containing the cofactors.
right. So in the igth place, you have the igth cofactor,
Right,
and
right. Yes.
then you just right,
Take the transpose.
and it doesn't come with the signs, right? Or does it come with the signs?
No, no. Cofactor comes with the sign, sir.
It comes with the sign, right? Okay. All right. Okay. So then what are you saying? The determinant of this.
Yes. So the determinant of this um, is equal to adjoint k.
Okay.
Yeah, the determinant of this is equal to the determinant of A
Is equal to determinant of A
times n minus 1. I mean, sorry, to the power n minus 1
to the power n minus 1.
to the power k, like n minus 1 whole thing to the power k. Yes.
This to the n minus 1 to the power k.
Yes, sir.
Okay.
Where n is the what n by n is the order of the matrix A.
Okay. Hmm.
So I thought this was interesting, and I
But why is
think
this true?
fairly. So you can have an inductive argument. Like I
Hmm.
did an inductive argument.
Yeah. So give us why
Uh,
this is true.
so first we'll start with
Wait, 1 second.
determinant.
Just a second. Nagesh, is the setup clear to you? What adjoint taking adjoint k times? So if you take adjoint once, you get a matrix, right? And by n, you have n by n matrix, you take adjoint once, you get an n by n matrix again. Again, you can continue to take adjoints as many times as you want. Okay.
Yes, yes.
All right. All right. Now, Aryan, go on.
So like it's obviously true for k equal to 0. Like so adjoint 0 would just be A. Then determinant of A is equal to determinant of A.
Right. This is just.
Right. Yes, sir.
Mm-hmm.
So now we suppose it's true for some t. Actually, I think we might need strong induction. I'm not sure. So we suppose that it's true for all 0, 1, 2, 3 up to t.
Okay. So
Then
we.
I've written it down. So can you give me a second? I'll just get my
Yeah, yeah,
proof.
yeah, yeah. I'll also
Yeah,
have
I'll
to just
just.
think about this.
Right. Yes, sir.
So Nagesh, try to tell how do you do it for k equal to 1? When k is equal to 1, then can you see this? Because that's a very important identity. Right?
Okay, okay.
Yeah. So when k is equal to 0, it's just determinant of a. Both sides become determinant of a. But when
Yeah,
k equal
correct.
to 1, you try to see what it is. Because that is very important.
Right. Yes, sir. I found it. Okay. Yes, sir. I found my proof.
Yeah. So tell.
Yes, sir. So now, since we assume it's true for some t, like just for ease of notation, all we can have capital T is equal to,
Mm-hmm. Capital T. Okay.
yeah, like I'm just calling it a matrix.
Mm-hmm.
Like a capital T is equal to adjoint to the power T of A.
Okay.
Right. And so from the induction hypothesis, okay, we keep that aside for now. And now adjoint of T plus one will just be adjoint of capital T. Like adjoint of T plus one of A.
Adjoint of T plus 1. Adjoint of means, okay, you mean adjoint T, this one.
Yeah, yeah. Adjoint of T plus one of A is
Mm-hmm.
equal to adjoint of T, capital T.
Right. So that is just by definition.
Yeah, yeah, by definition. So now we can take the determinant of adjoint T, and what we'll have is the determinant of adjoint T will be the determinant of T to the power n minus 1. So this is where like you sort of need strong induction because we're using the k equal to 1 case here.
Okay. So you're saying this is determinant of T to the power n minus 1.
Yeah, right. Yes, sir.
No, but so you're using strong induction, that is fine.
Yes.
But how would you prove this?
Which one, sir?
So how would you prove? So this is basically you're saying case for k equal to 1.
Right. Yes, sir. K equal to 1, but like instead of A, I just have T.
Yeah, that is fine. But my question is this a base case? No, because you have not proved it explicitly. Okay.
Yeah.
So
Yes, sir.
so you're saying this can be proved from the smaller cases. But
Right. Yes,
how
sir.
do you do that?
So now, so like once we have this, that determinant of T to the power n minus 1, then we can
No,
use the K.
uh,
Uh,
sorry, 1 second. Let me interrupt you. So why,
yes, sir.
but why do we have this? But why is this true? Like, why is case k equal to 1 true?
Okay, yeah. So we can like explicitly prove K equal to 1 case as well, like if we have to.
No,
Like I
and
know.
no, but the thing is, you have to. It
So,
doesn't
but
follow from case k equal to 0. See, because look at the nature of
no,
your
sir. Like
induction.
I'm using
Hmm?
strong induction. Like,
Uh,
I proved K equal to 0. Now I'm assuming that K equal to 1 all the way up to T, they're all true. So that like that I'm using that
okay,
hypothesis.
okay.
So that's why I'm using the K equal to 1, using that strong induction. And like again, I'll
Yes.
have to use the case K equal
No,
to
no, no.
T
That
because
is
we have this,
fine. Yeah, that is okay.
right?
So, yeah, maybe something very simple that I'm not understanding. So, case, so you are using all the smaller cases to prove the larger
Yeah.
case. Okay.
Yes, sir.
Now
Yes, sir.
tell
All
me,
the small.
yes. So, yes, but there's a problem, right? How would you prove? So, how would you use strong induction to prove k equal to 1 case? Tell me.
So because like it's true for 0,
Huh,
like adjoint to the power 0,
right.
then like okay, then it should imply, okay, 1 second, yeah.
There is a problem.
Actually, no, so like if we look at the standard proof,
Hmm.
I think it for like adjoint 1, like adjoint determinant of adjoint A, like
It
if
is
you look at
true.
this,
Yeah,
right?
standard
Yes,
proof is true, but I am saying that you have to state that or prove that. It doesn't follow from induction,
right.
and there is a difference, right? Because see, the problem is this, because when you're using strong induction, so what is strong induction? That you are assuming a statement so you're trying to prove a statement for n equal to k, and if you have
Yeah,
assumed the statement for all k less than n,
yeah,
okay?
right.
But
Yeah.
here you are always using k equal to 1 case, and that is a problem, right? If you are always using k
Oh,
equal to 1 case, then you are assuming, okay, let's say that there is not a problem, okay.
right, right.
If you're always using k equal to 1 case, okay, then it means that you are assuming that your t is bigger than k, is bigger than 1,
Hmm.
right?
Correct.
But
Yeah, yeah.
but then
Right,
that's a contradiction on its own, right?
right.
And even
So
even
yeah,
intuitively you can smell that there is something wrong in that
right,
yeah.
right.
Yeah, and obviously you don't get things for free, right? This is some theorem. Whether it's easy or hard, that's a relative thing, but this theorem has to be proved, okay? Or you
Right.
can quote it.
Yes.
I mean, this follows standard, okay? All right. So that is the point, that whenever you're using induction like n, then it has to be uniformly, like when you want to prove k equal to n case, you should use everything less than n. So it should be in terms of n minus something. Anyways, I'm just repeating the same thing. Okay, so this case,
Right,
but okay,
right.
fine. Let's move on, because that's the standard thing. So we assume that.
Right.
So
Yeah.
Nagesh, you can
Okay.
see that from here, from this identity, if you take determinant on both sides, then you actually get, right? But let's just show. So what we do is we assume this identity. So let me just go there. Well, actually that identity is very special. Even if you know the proof, you should still try to prove it, because it's a very nice one. So let's just quickly do this. So a times adjoint of a, okay, this is equal to, so 1 by determinant times identity. That just means that by definition, actually you can say that it means that it is like this, right? Where this the matrix where the 1 by determinant is on the diagonal. Okay. Or I mean, I'm just say doing the case where determinant of A is not equal to 0. If the determinant of A is equal to 0, then I suppose yeah, it becomes easy, right? So yeah, that we can deal with. We'll see that. Yeah, this now you take determinant on both sides, and then you can see that it is trivial. Okay. So this times determinant of this, and this one will actually become 1 by determinant of A. Okay, I think I did wrote the wrong identity, right? Yeah, it is. This is determinant of A, right? Yeah, this is
Yeah, yeah. Yes, it's
yeah,
not inverse.
yeah. Actually, that's why. Otherwise, you will have cases. Anyways, yeah. Then from here, same thing. The determinant of this thing becomes determinant of A, and this is somewhere places we get. I used to get confused with this, but you shouldn't get confused. Okay, it is this. If determinant of A is not 0, you can divide, and if it is 0, then you can try to prove that then this determinant will also be 0. And in that case also, then it is true. Okay. All right, so if there are no questions, then we'll move on. Okay, then what do we do next?
Yeah. Yes, sir. So like, kind of related. So from this, like, once I got this formula, I wanted to find a formula like of just adjoint of k, adjoint to the power k of k. But I think, like, I don't know, I tried some stuff, but then I didn't really get it, and then I just moved on because I had to study other stuff. But
Oh, so
what I
this,
got,
okay. So you mean for this solution of this particular problem?
no, so like this determinant thing is done. Now, like, I just want to find adjoint to the power k of a in terms of, smaller, so, like, adjoints or something like that I wanted to find.
Okay, okay, but my question is this problem done?
Yeah, yeah. Oh, yes, sir. So now,
Huh.
yeah, now we just use the t minus, I mean the t case, not the t minus one case.
Mm-hmm.
And then we get determinant of t is det a n minus 1 to the power t.
Mm-hmm.
which we are
Right.
allowed to assume.
Use the, yeah, you assume
So,
this. Okay.
right. Determinant of a to the power n minus 1 to the power t, and then this whole thing will be to the power n minus 1, so it goes inside, you get n minus 1 to the power t plus 1 as required.
Wait. Once I got confused. Oh yeah. Okay. So you're applying this to t. Yeah. You're just putting the value of t here. Right.
Yes.
Just put the value of
Yes,
t
sir.
and then it just happens. Right. Correct. That's true.
Yeah.
Right. So
Yes,
let's
sir.
just check the right hand side. The right hand side also works out. So this is true. And then the determinant of t, that is just what? That is determinant of adjoint of t times
No, sir.
adjoint,
Determinant. Yeah. Correct.
right?
Yes, sir.
N minus 1.
Yeah.
And this
Yes.
by induction hypothesis is equal to n minus 1 to the power t. But then we also have a n minus 1 here. And so that proves it. Good.
Right. Yes, sir.
Yeah, let me just think about this once. What happened? I mean, I can, yeah, determinant. So determinant and adjoint. Adjoint is being applied k times. And when you apply it once, you get this. Okay. Anyways, yeah. So then Aryan, where is the problem? You were saying that there is something you are not understanding.
Right. Yes, sir. So after this, I just wanted to find like a general expression for adjoint to the power k of a. Actually, I found one for adjoint cubed. Uh, so if you give me a minute, I'll just go bring that. Like it was
Okay.
actually a nice expression. So let me just
Okay.
go bring that. Yes.
Okay. I see. So he's trying to now find right. Yeah. Hmm. Yeah. So his question is that okay, we can understand the determinant of this matrix in terms of determinant of A, but can we understand this matrix, which is much more, right? So can we understand this matrix in terms of just A and maybe some determinants? Yeah, that is yeah. So adjoint of
Right.
A. Yeah. So what is it?
Yes, sir. So adjoint cubed of a.
Oh, okay, right. What is adjoint square?
Adjoint squared will be determinant of a to the power n minus 1 adjoint a. Like I think yeah, that's also like a standard one. Like it was in my book.
Right. Determinant of A to
N
the power
minus
n
2. Sorry. N minus 2.
minus 2. Wow. Times?
A.
Oh, okay. I don't know this. So let me just see. Let us see.
Yes, sir.
So adjoint of A is something that I know. Okay. I know adjoint of A, but then I don't know adjoint of A. So can you prove this?
Yes, sir. So we just apply like see adjoint of adjoint. Yeah. Now 1 second, sir. I need to work through this.
Hmm. Yeah, I can see it. I think it's interesting. Yeah, it kind of comes out of every row or something. The determinant comes out almost from every row. Anything? Oops. So the adjoint of A cofactors, right? So cofactor ij means you remove the ith row and ith column and you
yes, I
compute.
think I got it.
Right, what is it?
So we just use like B adjoint B is equal to det BI. Like where B I'm taking as adjoint A.
D times
Yeah.
adjoint D.
Is equal to determinant of D.
Right. So you use that good
Yeah.
old identity. That's important
Yeah.
identity. Okay.
Yeah. Now I'm taking D to be adjoint A.
But that
Like I'm just
is
calling.
not what we
No,
are
no.
doing. Okay. Okay. D to be adjoint A. All right.
Yes, sir.
Okay. Oh, no,
So
no. I'm
now,
sorry. I think you are doing correct. One second. Adjoint A. And here we get adjoint square A.
yeah, adjoint squared. Yes.
Mm-hmm.
Determinant adjoint A I. Like D. Yeah. Yes.
But here one should just mention that this is not square of the adjoint. This is adjoint applied to the
Yeah. Yeah.
matrix.
Yes. I haven't seen anyone use this notation. Like I just adopted it, but yeah.
Okay, okay. That's fine.
Right. Yes, sir. So now,
Maybe you can use
again,
like something like this.
yeah,
Like
something
a
like the
derivative
derivative.
applied time is different
Right.
from. Okay.
Yes, sir.
And
Right.
and then what do you do?
Uh, then, uh, then what we can do is like I'll give two steps in one. Like determinant of adjoint A on the right hand side, we just put determinant of A to the power n minus one.
Okay. Okay.
And then multiply by A on the left, or right, or yeah, left. Sorry.
Okay. Wait. You're multiplying both sides by A on the left.
Right. Yes, sir. But both sides.
Okay, I can see what you're doing. Right. So you're doing
Yeah.
this without really, using the definition of adjoint. You're using the properties only and doing it. Nice.
Right. Yeah. Yes, sir.
Okay.
So now A adjoint A will become det AI,
Hmm.
and then we would have isolated adjoint squared A. Not really, but yeah, adjoint squared A.
Hmm.
This side will become
These two can
uh
commute. This is just a number. Okay.
right. Yes, sir. So it'll become A.
Uh, okay.
Right.
So far so good. Then what?
Then we divide by
Determinant.
determinant of A.
Okay. What
Again,
if it is
we're
zero? What if it is zero?
so here I'm assuming that A is like non-singular.
Okay. Then it is true. Then you cancel
Right.
it and get it. Otherwise, then this formula should still be true, right? So
Right.
why is it then you have to just show that this is a zero matrix.
Yeah.
This is a
Right.
zero
Yes.
matrix. That's a wonderful thing. That's yeah. So then the task, so this is the beautiful identity we have got. We'll come to adjoint cube, but let's just discuss this a little bit. So you want to say that this is equal to zero, but let's not just yeah, maybe I will. Okay, I'm using this, which means adjoint applied twice. Let's not use that. That's a bit confusing.
Yes, sir.
This is equal to zero if A is singular.
Yeah. If A is singular.
Here we are just back and forth. We can use that singular means means not invertible and blah blah blah. Anyways,
Yes.
Yeah. Can this be done only with only with properties?
Which one, sir? This adjoint squared.
Yes, is equal to 0 if A is singular.
Okay. Well,
So you know already from all these formulas that A times adjoint of A is 0. Just from this formula. Right? If A is singular, then A times adjoint A is 0 matrix. But you want to show A is 0 matrix. Just doing it on a page. Okay, we are not 100% sure. I mean, maybe we are, but yeah. If this is given in the book, then this is probably true for non-singular also. Then yeah, how do we
yes, sir.
prove
Like it's given as a theorem in my
it?
book.
Yeah, so then we should be able to prove this. So this becomes cofactor of cofactors, and yeah, that should be 0, I understand, but how do we explain it?
So I think it's enough if we show that adjoint A is singular.
No, that is not true. Hey, why? Oh, maybe why is that enough?
So if you just consider this one, okay.
No,
Well,
it is enough. It might be okay. Even if adjoint A is singular, okay, fine. Then why is it enough?
uh, one, 1 second. So I think I somehow I got lost in my argument. Yeah. Yeah, right. Yes, sir. So now, like, if you just consider adjoint of A,
Hmm.
like again doing something similar, multiplying by adjoint A on the left.
Okay, multiplying by adjoint A on the left.
Yes, sir.
But from all
Then
this,
again
can you
use
show this? Like this original thing is 0. Okay.
no, like now, like again using the property, we'll get determinant of adjoint A I. Now, if adjoint of A is singular, then 0 times I will be O, like, or the zero matrix. So that's why I was thinking adjoint of A, if we show that it's singular.
No, I did not understand. What is
So
your
so now we have that adjoint of A times adjoint of A, like after multiplying on the left,
okay? So, but on the left of what?
or like just multiplying on the left of, if you just consider this
Okay.
expression,
Yes. Okay. Consider
then
this.
we use the property that this
Mhm.
thing will be equal to determinant of adjoint of AI. Yeah.
Right.
So now, like, yeah, right now we don't know that this is the zero matrix, but if we show that adjoint of A is singular,
Singular.
then we.
Hmm. Uh, yes, you're saying if A is singular, then adjoint of A must be singular. Yeah, that
Yeah.
should be correct. But even if you show adjoint of A is singular, that doesn't do it completely. Right? Then you get adjoint of A times this is product of two things is 0. Doesn't mean that one of it has to be 0.
No, sir. Like if you show that the determinant is zero, then it'll be 0 times in, which is
Hmm.
O. So I think so we should be done, right, sir? Like here we're not taking product of the matrices. We're like taking a number and I. So
No, no, yeah, this is a 0 matrix. Yeah, okay, then how do you
yeah.
show that this is 0?
No. Oh yeah, okay.
I
Okay.
mean, product of two non-zero matrices can be 0. So if both are non-zero, still the product can be 0.
Oh yeah, yeah. I forgot about that. Yeah, I shouldn't have, yeah.
Yeah, adjoint of A is singular. I can prove that.
Hmm.
But what do we do after that? So adjoint of A is singular because you have A times adjoint of A is equal to 0. This is right. And now
Yeah,
adjoint of A must be singular. If it's invertible, then A is 0.
yeah, right. So
Right. So because then you can just invert it, right? Right? To multiply by its inverse. And then A becomes 0, but
correct.
in that case also it is 0. So adjoint of A is singular. That is fine. Yeah. Okay, so less than a minute is left. So let us just end this again and just join maybe up to 5 minutes. Think about it, right?
Yes,
Join
sir.
in five
Yes, sir.
minutes. Yeah. So there's a time limit. So 5 minutes wait is there. Meanwhile, I'll also
Okay.
just
Yes,
write
sir.
in my notebook. All right.
Yes, sir. Yes, sir.